So the same two processes that we began to get familiar with in the last section we are going to just continue to repeat in this section. So last section, what we did is we got introduced to the positional place value system. And then from there, we did two things. We converted base 10 numerals into Babylonian and Mayan, which were different bases, base 60 and kind of base 20. And then we also converted the Mayan and the Babylonian different bases into base 10. We're going to do the same two things today, just with other bases, because other bases do have some applications and usefulness, and it also helps us to get to know the place value system. So here we go. I just want to first start, excuse me. First, just want to start with a reminder of the base 10 positional notation. Okay, I'm sure you're familiar with this. I'm sure you know this at an intuitive level because you've been immersed in this system. You've used it since you began learning how to count numbers. And so in the base 10 system, this is what our positions mean. Okay, we have our units. And then every time we count to 9 and we add one more from 9, we have a group of 10. So our next position is our 10s, our 10 to the firsts. So instead of writing out 10s, I'm writing 10 to the first. And then every time we count 10 10s, okay, if you had 10 $10 bills, 10, 20, 30, 40, once you have 10 10s, then you have a group of 100, which is 10 squared. And then 10 hundreds makes 1,000, 10 to the third, and we can keep doing this. You can write the positions forever and ever if you have the time to go ahead and do this. So 10 to the fifth, 10 to the sixth, and then I'm just going to use an ellipsis on the front just to indicate that we can keep following that same pattern on and on and on into eternity. Okay, well, given that, now what we can do, and we saw with the Babylonian base 60, they had units and then groups of 60s and then groups of 60 squared. That system became, the positions became big very fast. It's hard to do arithmetic with, and so what we're going to do is we're going to look at other common bases. So for instance, if I was working at something in base 8, so the anthropological assertion is that if human beings had been made with 8 fingers instead of 10, we would count in groups of 8 instead of groups of 10. So I don't know if that's true or not. People smarter than me talk about that sort of stuff. But what we're going to talk about is what would a base 8 positional system look like? Well, it would look like this. You'd have your units. And then what would you guess? If you just had to take a wild guess right now, what would your wild guess be to what the next position would be? Groups of what? Groups of 8. Every time you counted 8 of something, you'd have a group of 8. So 8 to the first. And then continuing on. Again, we're just making a wild guess here. We're just seeing how it's analogous to our system. What would be the next grouping? It would be groups of what? 8 to the second, or groups of 64. And then continuing, the next place would be groups of 8 to the third. So we think in terms of 10s, but it's possible to devise a number system in groups of 8s. So 8 to the fourth and 8 to the fifth, and then I'm just going to use an ellipsis because again, you could do the same thing on and on and on. Exercise 1, this is what I would like you to do. I would like you to propose what you think the first 5 positions, so these are 1, 2, 3, 4, 5, the first 5 positions of a base 6 system. What do you think those would be?
Yeah, I have a question about something on the homework. I took a picture of it. I can show it to you. After class, maybe is that?
You'll probably do all this.
Okay.
So we'll do it.
Okay.
No problem. Sounds good. first 5 positions of a base 6 system. So we're going to start, our rightmost position would be our units, as always. And then what do you propose? What would this second position represent? Groups of 6 to the first. Yes, every 6, you'd have a new group. And then continuing, this next position would be groups of 6 to the second, or every 36, you'd have a new third position. And then 6 to the third, every 216, the way we would think of it would be 216, but you'd have a new position there. And then 6 to the fourth, and that's 5. If you went further, because you're wanting to, there you go. That would be the first, I did the first 6 positions. I only asked for the first 5. One more, just to make sure that we're awake and paying attention. Exercise 2 says do the same thing, but this time do it with a base 2 system. Now, base 2, this is computer language, so this would be how computers think. So we're going to look at a little bit of that as we go. So you have your units, and then you have your 2's to the first, and then 2's to the second, 2 to the third, 2 to the fourth, 2 to the fifth, etc., etc. So we'll just keep going on and on like that. So just trying to give you an inkling on what the different positions are going to mean. So there's names for each of the popular different bases that actually get used very largely in the area of computers. So if you have what's called a base 2 system, I think that's the first one on the sheet that I gave you. A base 2 system is called a binary system. Binary means there's just 2 options. Base 8 is called an octal, O-C-T-A-L. It's called an octal system. Base 12 is called a duodecimal system. And then finally, base 16 is called a hexadecimal system. I'm not going to quiz you on vocabulary, that's not my style, but I like that you can have some awareness on what these different things are called in case you hear the words used or anything like that. So what if we're working with different bases then? What numerals do I use to represent my values in the different positions? Well, if you're thinking back, that is a fantastic question. So let's answer it. So firstly, let's remind ourselves of the numerals that we use in the decimal system. So the numerals for base 10. What are the numerals that we use when we write numbers down? What are they? 0 through 9, right? Would we all agree with that? 0 through 9. So then we start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many numerals is that, by the way? It's 10. Okay. Base 10 system, we have 10 numerals. And here's what happens. When you count a group of 10, now you start to recycle the numerals. Right? So then what happens, this is not one of the basic numerals, but then what happens when we get to the next one, we say is, okay, now I'm going to put 1 here for a full group of 10, and now I have no units. So I'm recycling the numerals. And so the same sort of thing is going to happen in all of these bases. So the numerals for base 10 are 0 through 9, and then we begin to recycle. So now the question is, okay, what would the numerals for base 6 be? There's going to be a 0, okay, because you can always have 0 of something. You can always have 0 in a place, okay. I will answer the thing in the blank in a minute. I want to follow the pattern, and then we'll go back up and fill in that blank. Okay, the numerals for base 6, it's going to start at 0. But here's the thing. If in base 10, when I go 0 through 9 and I get to the 10th one, I have a full group of 10. When do I have a full group in base 6? When I get to the 6th one, right? I get to the 6th, I have a full group of 6. So the numerals I need for base 6 are 0, 1, 2, 3, 4, 5. And then the next one would be a full group of 6. And I'm going to show you how we would write that in a minute. But notice for base 6, I need these numerals. I need 1, 2, 3, 4, 5. I need 6 numerals. So above the blank that I skipped, because this is the first time I've used these sheets and I'm still trying to see how things work, the place value system of base B, whatever the place value system, needs to have B numerals. Base 10 needed 10 numerals. Base 6 needs 6 numerals. So if you have base B, whatever the value of B is, you need to have B numerals. Whatever number that is, B is just a number. We're gonna count something in a different base in just a minute. But I just want to let you know how this works. So I'm counting. I only have 6 fingers. Okay, I go 0, 1, 2, 3, 4, 5. Now the next one is a full group of 6, right? So if you were immersed and lived and worked with and always did your arithmetic base 6, here's what you would do. Your next one would be just like ours. You would have a full group of 6, and then you would have 0 units. Now, to distinguish this in this class, because this looks just like this, and I don't want you to confuse them, what we're going to do when we're in other bases is we're going to put a little subscript here. So we're going to put a little base 6 right there, just so that you know that this is 1, 0, base 6. So this is a full group of 6 and 0 units. Well, the numerals for base 4. Well, I want you to just make a hypothesis. So just list out what you think, how many numerals that are needed for base 4. But I told you in general, the general principle is when we were base 10, we needed 10 numerals, 0 through 9. When we were base 6, we needed 6 numerals, 0 through 5. So that means base 4, how many numerals do I need? 4 of them. So that is 0, 1, 2, and 3. And then when you get to the next one, you'd have a full group of 4, and you would begin using your places. You'd begin recycling. Where it gets nice and fun and interesting is the next one, example 2. What we're going to do this one together. Actually, do the next 2 together. We're going to list the numerals for base 12. Well, according to the general principle I gave you, if I have base 12, how many numerals do I need? 12 of them. Okay, so this is what tends to, now if you grew up on a planet that was base 12, you have all of your numerals, you wouldn't even think twice about this. But since this is novel for us, we have to, this is how math people, computer people, anybody using base 12, that they would do that. They start at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 numerals, but now I run out of 1-digit numbers. So here's what happens. Because in base 12, you don't start using positions till you've counted a full group of 12. Once you have 12 of something, you tie it up, it's a full group. So what you're going to use now, the next numeral is going to be the letter A. A means you have 10 of something. That's how we would think of it, right? Is 10 of something. Okay, so A is, you got 10 of something. And then B is you'd have 11 of something. Those are the numerals. Because we would have to have 1 single-digit numeral for every possible value that we could have. And then if I went one more in base 12, I'd have a full group of 12, and I would put a 1 for a full group of 12 and a 0 for units. We begin recycling the numerals. One more unfamiliar one. For base 16, again, same question. I have base 16, I'm going to need 16 numerals. Well, we already know the first 12 of them, so let me just rewrite these. Then I'll pause and let you catch up to me. So if you're using base 16, you need 16 numerals because you don't start counting, you don't start using your places, so you have a full group of 16. So here we go. So we said 0 through 9, and then the letter A represents 10 of something, B is 11, so then we're just going to continue alphabet. C is 10 on 12, D is 13, E is 14, and F is 15. There's my 16 numerals. Now, as far as how we work with them, we're going to do some examples. And I know this is difficult stuff because, again, you're thinking about things brand new. You're unlearning, and relearning. So this is definitely something we've got to practice a bunch of, and we're going to. So at the top of the next page, I want you to be super happy. So subliminally, I put a bunch of smiley faces there. And so if we were counting this base 10, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. So give me a moment. Lost count. I think that's 14. So I've just transcribed the same number of smiley faces on the board. And so, again, I just want to remind you how numbers are working, okay? So what we would say is this is 17 smiley faces. It's one group of 10 and 7 more, right? So the first 10 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first 10 of them, that's my group of 10. And then this is the 7 more. And I have a partial group of 10. That's what 17 means. Okay, so in our nomenclature, in our decimal system, we will write this 17. But here's what we're going to do. We are going to count these in example 4. We are going to count these in base 8. So what base 8 means is that every group of 8 it is a new place. Okay, so every group of 8. So here's what I'm going to do this 2 ways because I'm trying to see which way you're going to understand this, and hopefully it's going to break in there. If I'm doing base 8, here's what I've got. I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 1, 2, 3, 4, 5, 6, 7, 8. And then I've got 1 left over. So if I'm writing this in base 8, if we were thinking in base 8, then what I have is, how many full groups of 8 do I have? 2. How many units do I have? 1, base 8. So this represents the same number. Remember, number is the how many, but it's communicating it differently. We're communicating it in a different base 8. The way we would count, you don't have to write this down, but again, I'm just trying to get some neurons to fire in your brain. The way you would count base 8 is like this. Okay, you would say, okay, I have 1 smiley face, 2, 3, 4, 5, 6, 7, 8, 8, no. Yeah, I have 1, 2, 3, 4, 5, 6, 7. Now I have a full group of 8. And we don't have the numeral 8 in base 8 system. So now, at this smiley face right here, this person, I have 1 full group of 8 and 0 units. And so now the next group of 8, this would be, I'm not putting a little base 8 just to be faster. Now I've got 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. And now this one is my second full group of 8. You can see that from the underline. So now instead of, again, we don't have a number 8. If you were living in base 8 world, you wouldn't have it. So now this is 2 full groups of 8 and 0 left over. And then that means this last happy face is the 2, 1. And that's how you would count in base 8 if that's how you learned arithmetic. So here's what I would like you to do. Okay, we're gonna do this a couple times because I know this is difficult, and I want to see if you can get used to it. I want you to do the same thing that I just did, but I want to know what is the numeral representation of these smiley faces in base 6. Okay, what is it in base 6? Okay, in base 6, it's every group of 6 that matters. Okay, that's how we're going to bundle everything up. This is our regrouping. So here we go. I'm going to underline. I've got 1, 2, 3, 4, 5, 6 to here. I've got 1, 2, 3, 4, 5, 6 to here. And then 1, 2, 3, 4. I don't have another full group of 6. So if I was representing this number of smiley faces in base 6, how many full groups of 6 do I have? 2. How many do I have left over? Okay. So it would be 2, 5, base 6. That's how you would count that. And again, this next part, you don't have to write this if you don't want, but I'm just trying to get the juices flowing here. So we've got 1, 2, 3, 4, 5. Then this is my full group of 6. So that would be 1 full group of 6 and 0 left over. And then 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. And then here's my smiley face. That's the next group of 6. So that would be 2 groups of 6 and 0. And then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. That's how you would count in base 6. Let's do this one more time. Take the smiley faces now, and we're going to do a base above 6. I would like you to do the same thing. Count those smiley faces, base 12. What number or what numeral base 12 would represent this number of smiley faces? Base 12. So in base 12, every full group of 12 is another full group. So here we go, my smiley faces. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 right here. That's a full group. And so how am I going to represent this number of smiley faces in base 12? It's what? 1 full group of 12, and then 5. I put a little 12 there. This, again, if you were raised in base 12 world, this is how you would count. You go, okay, that's That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we have a single numeral for each of those. Now this one represents my full group of 12, so that's where I have a full group of 12 and 0 units. And then 1, 2, 3, 4, and 5. And that's how we ended up with that. Okay. You doing okay? I know, it's funky. I totally get it. The first time I ever saw this, I was like, okay, that's great. And but the more we use it, the more we process it, the better it is. So now what we're going to do for pretty much the rest of our time together is we're going to do the same thing that we were doing with the Babylonian and the Mayan numbers. We are going to take the first few examples, we're going to take other bases and convert to base 10. Can anyone remind me, this was on the sheet from last time. Can anyone remind me what the standard procedure is to convert from other bases to base 10? What do we always use? Expanded notation. That was the little note that I had at the bottom, I think, of page 1 of the previous day. So if you need to remind yourself of that again, that's fine. Over to the side of example 5, right? To convert to base 10, I use expanded notation. It's the same exact thing we were doing before. While you're doing that, I'm going to write down example 5. We're going to convert 312 base 4. We're going to convert this to a number we would recognize and be able to understand the size of. So if I said to you on the way in, I'm going to give you 312 base $4. What have I just promised you? How many dollars are you going to get? Okay, well, to see that, we're going to use expanded notation. And expanded notation says this 2. What does that 2 represent? It represents units plus, this is base 4, so the 1 represents groups of 4 to the first, and then the 3 represents groups of 4 to the second. That's why on the first page I don't know if we did it for base 4, I don't remember, but for a few different bases, we listed out what the positional values mean. So we're just doing that for base 4. So I'm going to put some parentheses around this just so it's a little easier to read. I've got 2 units. I've got 1 group of 4. I've got 3 groups of 4 squared, or 16. And from here, it's just to calculate a problem. 3 times 16, that I think is 48, if my arithmetic is correct this afternoon. 1 times 4 is 4. 2 times 1 is 2. And so 48, 52, that's 54 is the number we would recognize. That's what 312 base 4 represents. So I'm going to give you a couple minutes. Exercise 7. Okay, I would like you to take exercise 7. It's 6053 base 7. I want you to convert that to base 10, please.
just looked at it. I saw a picture of it, so.
This problem is base 7. So remember, we're dealing with base 7 positional values. So I'm going to start at the right side of the number. The 3 means I have 3 units. So 3 times 1, just to remind myself it's units. Now the 5 means I have 5 groups of what? Perfect, 7, thank you very much. And then 0, I have 0 groups of 7 squared, great. And then finally, I have 6 groups of 7 to the 3rd power. Once you've done that one, so the skill here, when you're converting to base 10, is remembering what the positional values are. Once you've done that, you grab your calculator, and 3 times 1 is 3, 5 times 7 is 35, 0 times anything is 0, and then what is 7 times 7 times 7? Is that 343? 7 to the 3rd? So then 343 times 6 is what value? 2058. Okay, I'm glad got agreement on that. So this was 343 times 6. That becomes 2058. And so now I add these up. 35 and 3 is 38. When I add that here, I get 20. Is that 96? Did I add that right? Yes, it's always suspect when I'm doing it in my head. So definitely double check me and shout out when I'm wrong. If you have a question about this, okay, I know this is funky and different, and you probably should have questions. Please ask it, and as you're meditating on that, do exercise 8, base 2, 110010, base 2. So this number here, that's base 2, just going to start. So this 0 that's on the right, that means I have 0 units. So 0 times 1. Then this next one is I have 1 group of 2 to the 1st power. Then I have 0 groups of 2 to the 2nd power. Then I have 0 groups of 2 to the 3rd power. Now, if you can get by without writing the ones with the zeros, that's great, but I sometimes lose my place, so I like to write them out. I haven't left myself enough room because just messed that up, so I'm going to do the next one right down here. So then I have 1 group of 2 to the 4th power, and then I have 1 group of 2 to the 5th power. So what this means is in your calculator, when you type the following number that we're going to come up with down here, the calculator represents it in its memory as 110010. That's how it thinks and does arithmetic. That causes some problems. I have an article about that, and if I remember, I hope I remember, I'll copy it down and bring it in. So here's what we've got. We've got 0 plus 1 times 2 is 2, plus 0 plus 0 plus 1 times 2 to the 4th. 2 to the 4th is 16, if I'm remembering right, and then 2 to the 5th is 32. So I have 0 plus 2 plus 0 plus 0 plus 16 plus 32. That is the number 50. We all get the same thing there? So on your Apple calculator, you put in the number 50, it represents it like this, and then it does its arithmetic with it. Okay, one more going this direction. So if you have a question about converting a number to base 10, you are getting close to the time to make sure you ask that question. So this is 4A3 base 12. Get what? Well then, so you got this part right here? Yeah. Okay. So then I just use my calculator to get the numbers. 0 times 1 is 0. And this is 1 times 2, that's 2. 0 times 4 is 0. 0 times 8 is 0. 1 times 2 to the 4th, 2 to the 4th is 16. 1 times 16 is 16. And then 1 times 32 is 32. And then you just add up those values. So 16 and 32 is 48. 0, 0, and then 2 is 50. And that's where that 50 came from. So I just actually did the multiplying together, just like we're going to do on this one. After we're going to write this one in expanded notation and then multiply things together using our calculator and then add it up. So on this one, again, the 3 means I have 3 units. Okay, so 3 times 1. The A, now let's convert this A to what we're familiar with, because I don't know about you, I don't think in terms of A. So we said that in our duodecimal system, A represents how many? Okay, A represents 10 of something. So that is 10 groups of, and what does this place value represent in base 12? 12, yeah, 12 to the 1st. Okay. So it's 10 times 12 to the 1st. The A represents 10, and then the position, the A is in the position of 12 to the 1st, plus then I have 4 times, the 4 is in what place value? Okay, 12 to the 2nd. So since this one's base 12, we have 12 to the 1st, 12 to the 2nd. The next one, if there was one, would be 12 to the 3rd, on and on and on. And again, at this point, we just use our calculator. 3 times 1 is 3. 10 times 12 is 120. And then 12 times 12 is 144. So 4 times 144 is, what was that? 576. Do I have confirmation? Are we good? So 576 plus 120, that's 696. Plus 3 is 693. That's how we would think about and recognize the number. That's how base 12 would represent that same value. Yeah.
699.
699 is even better. Before I move on, any questions about converting from another base to base 10? This is the same process we used when we did Babylonian numbers. Okay, and they had just 2 numerals, which is good, better than having 60 numerals. And in Mayan, we did the same thing. Yeah.
There's like a base that goes beyond like the letters of the alphabet.
You would just, whatever, we just use the letters of the alphabet because they're convenient. You would use whatever symbols you want. You could use anything. It doesn't matter. I don't know that anybody uses a base that is big enough to run out of numerals. So we can look up the answer to that question and see what it would be. Yeah, but so yeah, we just use these. So our numerals, remember in the Hindu Arabic system, our numerals, the 0 through 9, have their basis. They originated in India. Okay, so and then a mathematician named Fibonacci came across those in Europe, and he started using them. And then there's a period of time where math went down into Africa and got saved and got refined. And so that's where the Arabic part of it came from. The numbers that we have came out of that, but there was a development process. So they just occurred. Those were the symbols people associated with those numbers, but they could have literally been anything, right? So the actual shapes of the things absolutely does not matter. You could use anything that you wanted. If you were going to invent a new number system tomorrow, you could use whatever shapes and symbols that you wanted. All right, we're going to finish up this section by doing the reverse process now. The reverse process is where we start with base 10, and we're going to go to another base. So my example is example 6. I'm going to convert that number to base 12. And while I'm erasing, does anyone remember what we said in the last section for how you take another base, or excuse me, how you take base 10 and write it in another base? What is it that you do? What's the process? I'm sorry, the wind. Yes, we regroup, okay, by using the new place values. So when we were doing you remember when we were doing this with the Babylonian, we listed the place values right here. We said, okay, we had our units, and then we had our 60s, then our 60 squares. Well, we're going to do the same thing here. We're going to be consistent with our process. Okay, so this first problem, example 6, I want to take 2,315. That's my number. I understand what that is, and I want to write it base 12. So first thing I'm going to do, because this is new and different and awkward, is I'm going to list out what are the place value representations for base 12. And remember, we're going to stop listing them when I get to something that's bigger than this, okay? Because I want to be able to divide into this and regroup. So for base 12, I have my units. That's great. Then the next place is my groups of 12 to the first. Then my next place is groups of 12 to the second, and 12 to the second is 144. Okay, 144 is less than this. I can regroup, I can make that, but let's keep going. Let's see if that keeps happening. Then I'd have groups of, after 12 to the first, 12 to the second, I have 12 to the third. Now you're gonna have to help me. 1728, we're all prepared. Okay, so 1,728. Okay, I can divide 1,728 into that. I can make a full group of 1728. Now, the answer is going to be no, but I'm just going to verify that I can't go another place value. So 12 to the 4th, what is 12 to the 4th? Large. 20,736. Did I hear you right? Perfect. Well, okay, that is bigger than this. I can't make a full group, so I don't need that, but it's always good to verify, just to be sure. So step 1, I'm just writing down the places. And now step 2 is I regroup. So I'm going to start with the 1728, and that's going to go into 2315. Well, that's just going to go in one time. 1 times 1728. I'm gonna throw out my calculator because I'm feeling mathematically lazy today. So my calculator says 2315, stop texting me, minus 1728 is 587. So my first place, my 12 to the third, I have one group of 12 to the third. We'll write this in a way that we're used to, but this is my process. I do the same thing every time, so I'm used to it. So that's why I'm showing you to do the same thing every time. Now I'm going to take the 587. What am I going to divide into the 587 now? I'm going to just go down the ladder. I'm going to divide 144. And it looks like 144 is going to go into that. I'm going to try 4 times. I'm going to be an optimist. 4 times 4 is 16. 4 times 4 is 16 plus 1 is 17. And then 4 times 1 is 4 plus 1 is, oh, I did it. Yes. So that means I have 4 groups of 144, and then my remainder is 11. So sorry? It will be, yes. So do I have enough? So normally we would take this remainder and divide the next place. Do I have enough to divide the groups of 12 in? So I don't have any groups of 12, and so my remainder is actually my units. I've got 11 units. Now we're ready, just like we did with Babylonian, we're ready to write that number. Yes. I'm doing my work in my way of thinking. You and Paula said the same thing. You're totally 100% right. You're just way ahead of me. But I'm just writing this down in my way of thinking. And now we're going to convert this to base 12 nomenclature. So here we go. I've got 1, I've got 4, I've got 0, and then yes, you're not going to write an 11 now because that's base 10, that's base 10 stuff. So the way we represent this in base 12 is a B. And then I'm going to put a little 12 there to let everybody know that that's a base 12 number. And there we go. That is the answer. Great. So flip the page. If you would do the next one, please. It's the same sort of thing, except I think this time I've changed the base. Yes. You're going to write 273 in base 3. So just to give you a nudge, I'm going to write the bases, the place values right here, in case you're struggling with that. So keep working. We give you a little more time. But my base 3 positional values are these. Right, so the place values, the positional values in base 3, I've got my units, my 3 to the firsts, my 3 to the seconds are 9, groups of 9, 3 to the thirds, 27, 3 to the fourths, 81, 3 to the fifths, 243, and then 3 to the sixth is 729. That's too big, so I don't need to worry about that. So I'm going to start with the 243. So I'm going to divide 243 into 273. That goes one time and leaves me 30 left over. So I have one group of 243. Since I have 30 left over, I do not have enough for a group of 81, so I have 0 of those. Now I'm going to divide in 27. 27 goes into 30 once, leaves me a remainder of 3. So I have one group of 27. Again, the next place value is 9. I don't have enough, so that's 0. And then I have a remainder of 3. If you need to do the work, take my remainder, put it there, and that goes one time and leaves nothing. So I have one full group of 3, and then I have no remainder, so I have no units. So now I'm going to write this down, and if you got any question, if you stumbled on something, I don't blame you. It's difficult stuff, so let me know. But I have 1, 0, 1, 0, 1, 0. Pretty repetitive number. Base 3. Big thing there is seeing that after you divide the 243 to 273, your remainder is 30. You don't have enough. You don't need to divide by 81. You can skip that, but don't forget to put your 0 there. That's the whole point of place value system. Question? Anybody got one? Got 2 more for you. So we're getting close to, by the way, we're not meeting Monday. College is closed on Monday. So just before I forget to tell you that, let me do that. All right, exercise 11, you're going to convert 85 to base 2. So I've written out the positional values here. We've got our units, our 2 to the first, 2 to the second, third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh becomes too much. I don't have 128, so I don't have a full group of that. So I'm going to start with 64. So 64 is the first positional value that we're going to occupy. So 64 goes in 85 once and leaves 21. Okay, so I have one full group of 2 to the 6th. My remainder is 21. So what's the next thing I'm going to divide into this? 16. So I don't have any groups of 32. So I'm going to divide 16 into this. So 16 goes into 21, goes once. Okay. So then I have 5 left over. So because there's 5 left over, what am I going to divide in next? 4, 2 squared, so I don't have any 8s. So now when I divide 5 in, or excuse me, when I divide 4 into 5, it goes once, leaves a remainder of 1. So I have one group of 4, I have no groups of 2, and I have 1 unit left over, which is good because the only numerals we use in base 2 are 1s and 0s. So 85, how does your calculator code 85 when you put it in? Well, it codes it like this: 1 0 1 0 1 0 1 base 2. Although the calculator doesn't put base 2, it already knows that. Last one for the day, and then I think we've got a couple questions about the homework, so we'll take care of those. So the last one is 6893. Convert that to base 16. All right, here goes. Here's my place values. I've got units. 16 to the first is 16, 16 to the second is 256 in our way of thinking. 16 to the third is 4,096 in our way of thinking. And then 16 to the fourth is too large. I can't regroup. So I'm going to start with the 4,096. I'm going to start with the 16 to the third place. 4,096 goes into 6893. Looks like that's going to happen once. Oops. And when I do my subtraction there, anybody want to tell me what's left over? 2,797. Do I have confirmation? You're doing good with that? Excellent. Okay, so I have one group of 16 to the third, and we're off to the races. Next is 256 that I divide into 2797. So 256 goes into 279 once. Bring down the 7. And then it doesn't go into that at all. Okay, so I have 237 left. Now, if you're quick on your feet and you're ahead of the game, then you can write an A here. I'm just going to write a 10. Okay, just one step at a time for me. The next thing I'm going to do is divide 16 into the 237. 16 goes into 23 once, and that leaves 7, and I bring down the other 7. 16 goes into 77. It looks like that's going to be 4 times. 6 times 4 is 24, so that's 64, and that leaves 13. Did I do that right? Yep. Okay, lovely. So this is 14, and then this is 13 left over. And now we will write this as a base 16 number. Are we good up to here? Okay, so my first place is 1. My second place is A. My third place is, what's that, E? And then what comes before E is D, I guess. So there you go. That is your base 16 number when you convert it to the appropriate numerals.